Okay, so conditional and classical probability. So if the probability of A equals 0.2 and the probability of B equals 0.1, what's the probability of A union B if A and B are independent? First off, I see this. I see that union and I think or. And I also think addition, and specifically I think about the general addition rule. And with that in mind, I'm going to write that down. So I have the probability of A union B equals the probability of A plus the probability of B minus the probability of A and B. All right? But then they tell me something else. Hey, A and B are independent. And I go, oh, that's good. That means the probability of A and B equals the probability of A times the probability of B. All right? And I go, that's nice because that means I can substitute this right here using some really fancy algebra that I learned at some point from a teacher I will never mention again. Probability of A union B equals the probability of A plus the probability of B minus the probability of A times the probability of B, because I just substituted in. All right? Well, they tell me A is 0.2. They tell me B is 0.1 minus 0.2 times 0.1. When I do all my fancy math that I've written off to the side so I don't mess it up and you don't have to wait for me to punch all the buttons in the calculator, I get 0.28. And truthfully, if Mrs. Lamb and I are grading your paper, we're going to want to see this and we're going to want to see this. All right, we're going to want to see those things. Okay. The next question, number 2. Suppose the probability of X equals 0.25 and the probability of Y equals 0.40. Now we have the probability of X given Y equals 0.20. What is the probability of Y given X? And I immediately, my head starts to explode when I see all that stuff. And I go, you know what? I'm not smart enough to figure all that out, okay? So I'm not smart enough to figure all that out, so I start writing formulas down. I go, what do I know? Well, what I know is the probability of X given Y equals the probability of X and Y over the probability of Y. That I know, okay? Don't know much, but I know that. So it's like, all right, so let's start plugging in what I know. Well, I know that this is 0.20 equals, and I'm just going to use the intersection symbol to abbreviate, speed up my writing just a little bit, over 0.4. That means 0.08 equals the probability of X and Y. Now I have this mess over here that I haven't fooled around with, and this is what they're actually asking me for. So I have the probability of Y given X, which is the probability of X and Y over the probability of X. Well, guess what? I know my intersection is 0.08 because we just solved that. So this is getting plugged in right there. And they told me X is 0.25. And guess what? I've done my work. So now the probability of Y given X equals 0.32. All right. Given the probabilities A equals 0.4 and A union B is 0.6, what is the probability of B if A and B are mutually exclusive? I love this problem. First off, as a reminder, mutually exclusive, there is no overlap. So if they're mutually exclusive, then my intersection equals 0. Now, once again, they've given me this formula. I mean, they've given me union, A union B, so I'm going to write down the general addition rule. Well, they tell me A union B is 0.6. They tell me A is 0.4. I don't know the probability of B, but I know that there's no overlap because it's mutually exclusive, so this is 0. I'm pretty sure I can actually solve this. Subtracting from 0.4 from both sides, I end up getting 0.2 equals the probability of B, and that's if they're mutually exclusive. Guess what? Can't leave it well alone. We also have to do what if they're independent. So once again, the probability of A union B equals the probability of A plus the probability of B minus, and I'm just going to put the intersection symbol right here. Please remember, the intersection, probability of A and B equals the probability of A times the probability of B under one condition. This is only true if independent. It's only true if independent, but they said, hey, it's independent. They tell me it's true. So at which point it's like, okay, let's start plugging in. Well, I know this is 0.6. I know A is 0.4. I don't know the probability of B. All right. Minus, I know A is 0.1, but I don't know the probability of B. Well, I'm going to subtract this real quickly, and I get 0.2 equals the probability of B minus
0.4.
Oh, excuse me, that's not a 0.1, this is a 0.4. Excuse me about that. Is that what you're about to say?
Yeah.
Yeah. So this is a 0.4 because this is A minus 0.4 times the probability of B. If I remember correctly, I'm going to simplify this up just a little bit. B minus 0.4B, just because this makes things easier for me to see. This has a coefficient. That coefficient is 1. So 0.2 equals 1 minus 0.4 is 0.6B. Divide both sides by 0.6, and I end up getting B equals 0.33, and I should put the probability of B as 0.33. Okay, so real quickly, because I kind of made an error there, this represented the A, because this is the probability of 0.4 times the probability of B, and that doesn't show up on the screen either. Sorry about that. Probability of B, and that 0.4 came from the A. And I apologize. I may need to come back and talk about that in just a moment. Moving on to letter E. Given that the probability of E is 0.32, probability of F is 0.15, and E union F is 0.422, are event E and F independent? So, first off, I see this. So, as soon as I see that, I'm going to go general addition rule. I'm going to write it down. So, the probability of E union F equals the probability of E plus the probability of F minus the probability of E and F. And by the way, this is just a starting point. Even if I don't know where I'm supposed to end up, that's where I'm going to start with. I don't always try to figure out everything. I want to organize and see what I have and see what I'm missing. So immediately I see, okay, well, I have 0.422 here. I have 0.32 here. And I have a 0.15 here minus my intersection. So I end up with 0.422 equals 0.47 minus my intersection. So I end up with a negative 0.0488 equals, and people start freaking out because they see a negative sign and they think they messed up. But it's, oh, we have a negative intersection. Change the signs. All right? Divide by the -1. So the probability of E intersect F equals 0.0488. And the reason that was important is, first off, we knew we were missing this piece. Now, can I use that piece? Well, they asked about independence. All right? And if things are independent, the probability of E times the probability of F equals the probability of E and F, or E intersect F, equals if they're independent. Well, E is 0.32, F is 0.15, and the intersection is 0.0488. And guess what? 0.0488 equals 0.0488. The events E and F are independent. I'm just going to abbreviate IND. They are not related, or they are not associated. All right? Okay, I'm going to pause this thing real quickly. The melon scenario. A grocery store purchases melon from two distributors, J and K. Distributor J provides melons from organic farms. The distribution of diameters of melons from distributor J is approximately normal, with a mean of 133 and a standard deviation of 5. A randomly selected melon from distributor J, where is I'm sitting here with the wrong stuff. Thank you. From distributor J has a probability of 0.21 of having a diameter greater than 138. Distributor K provides melons from non-organic farms. The probability is 0.84 that a melon selected at random from the distributor K will have a greater diameter than 138. For all the melons at the grocery store, 70% of the melons are provided by distributor J and the rest are from distributor K. I read that problem, and I reread that problem, and I reread that problem, and there is a ton of information there. And I need something to organize it. So I really do. I start looking for an organizational tool. Whenever I have a ton of stuff, I start looking for an organizational tool. And sometimes I'll start making a table, even if it's doesn't end up being the right way to go, just to organize things. So just to organize things, I'm going to start making a table. I mean, yes, I know that that's what we needed to do, but I really do sometimes just go out on a limb and go, you know what, we're going to make a table and just to organize things and see what we have. So a grocery store purchases melon from two distributors, J, etc. We have, and we look at the numbers with a mean of 133, standard deviation of 5. A randomly selected melon from distributor J has a probability of 0.21 of having a diameter greater than 138. As soon as I look at this, I go, you know what? This right here is associated with two variables. It's associated with coming from a distributor and size. That makes me think, you know what? I have two different variables here. I have K and I have distributors and I have size. So this might be a table problem. Distributor K provides melons from non-organic farms. The probability is 0.084 that a melon selected from random from K will have a diameter greater than 135. Once again, this is a two-variable number. This is a two-variable number. And when I'm doing a table, I need to find the variable or the number that's associated with only a single variable. It's critical. Once I find that one, the table goes together fairly well. For all the melons at the grocery store, 70% are provided by J. and the rest from K. 70% go to distributor J. Nothing about size. This is a distributor, so this tells me this 70% goes right here because it's associated with one variable. This number right here is the most difficult number of all. It's always one whole. So 1 minus 0.7 is 0.30. Now, this was associated with distributor J. This is associated with distributor K. I don't even know where I'm going yet, but because I know this number goes here and this number goes there, I'm going to write them very small right here, and I'm just going to bring them up. Once again, not even sure where I'm going. I haven't even determined what I'm going. All right? So we have size. All right? So we have greater than 138 and less than 138. And that's, I know that because I've read the problem a couple times. We'll have a greater than 138, and over here, greater than 138. So we're dealing with 138 as kind of a size. Well, looking at this first one, a randomly selected melon from J has a probability of 0.21 greater than 138. So J and greater than 138 is here. So this is going to be 0.21 because this is the intersection of J and greater than 138. 1 minus that is 0.79. I'm going to go ahead and multiply this and this and this and this, and I get 0.147. And right here, I end up getting 0.553. Moving right along, the probability is 0.84 that a melon selected at random from distributor K will have a diameter greater than 138. So this is K and greater than 138, which intersects right here. And 1 minus 0.84 is 0.16. Multiplying this times this, I end up getting 0.252. Here I end up getting 0.048. Adding these two numbers together, I end up getting 0.399. Adding these two numbers together, I get 0.601. Now, if I've done everything correctly, these two numbers sum to one whole. This number plus this number sums to 0.3. This number plus this number sums to 0.7. This provides a really good check for you, all right? A really good check. So for a melon selected at random from the grocery store, what is the probability that the melon will have a diameter greater than 138? Well, guess what? I've showed all my work when I made the table. So this answer right here is just 0.399. It came straight from the table. I have no other work to do. It's right there because I did the work on the table. Question number 6. Given that the melon selected at random from the grocery store has a diameter less than 138, and by the way, we see the word given. And as soon as I see that word given, I immediately think this. I go given, and then I look for intersection. All right, so that's what I know. I'm looking for that. And in this particular case, we're looking for less than 138. So this right here tells me my denominator because we're given in this less than 138. What is the probability the melon will be from distributor J? So I circle the J. Here's my street intersection, which is 0.553. And this should equal about 0.92. All right, I'm going to run out of room here, so I'm going to use some sticky notes. What is the probability that a randomly selected melon has a diameter less than 138 and was from distributor K? and means intersection. So we're looking for the intersection, but this time we're looking for an intersection based on less than 138 and distributor K. And by the way, this is out of the entire population. There's no given. Less than 138, distributor K, that's my intersection. I know that looks beautiful with all that circling. So this answer right here for number 7 is 0.048. And once again, we did the table work, and it's just that intersection of K and less than 138. Finally, given that a randomly selected melon came from distributor K, so we're told it came from K, and by the way, they said the word given. As soon as they say the word given, I was like, you know what? It's going to be in the denominator. So given, and I know I'm going to have an intersection. They said from K, well, K is 0.30. What is the probability that it has a diameter greater than 138? Well, my greater than 138 is up here, so this is going to be 0.252, and this happens to equal 0.84. All right? Okay. The distribution of the diameter of the melons from K is approximately normal with the mean of 144 and a standard deviation of 7. The distributions of the melons from J and K are independent. What is the mean difference? Well, what did they tell me? They want K minus J. We're looking for the mean. And they tell me K has 144, and up here J was 133. Equals 11, and that's all the work you need to show on that. The next thing, it says, what's the standard deviation of the difference, K minus J? So we have the standard deviation of K minus J. Well, this, first off, J has a standard deviation of 5, and K has a standard deviation of 7. And right there, you should be saying, Mr. Spencer, you cannot subtract standard deviations. All right, not allowed. We have to convert them to variances, and we have to sum them. All right? And then when I do that, I end up getting about 8.6. I get about 8.6. So it should be, can't subtract the standard deviations, we have to sum them. So 7 squared plus 5 squared is 8.6. All right.